Okay, so we wait for the sound on stage. I am talking right now, so louder, louder. Test, test. This is a test. Okay, well, that's good to know. So whenever I can start, you give me a cue.
Mark, can you hear me?
Yes, so Mark, hi. Yes, I can hear you.
Yeah. Okay, we are ready. You can share your slides and start your presentation. Thank you.
Okay, thank you very much. So this is my cue. Welcome back, I should say, I guess. Though I just started, but good afternoon. Um, Thank you for joining. So I will talk a little bit about my contribution to the project. Part of the project is of course about sea level, and we're talking about sea level close to Bangkok, but also sea level in the Gulf of Thailand, as we measure with spaceborne altimetry and from the use of local tide gauges. And I will be talking a little bit about what's happening in the Gulf of Thailand. And I do this together with my colleague Vince Simons. Uh, he is actually present at the workshop, and let's see how this works. If I can get it to work. Okay. So yes, we're talking about sea level. Uh, Question is, why would you study sea level? Why is it important? Well, basically, water is all around us. It's like more than 70% of. Okay, so maybe should I get a cue louder? Should I talk louder? I can try to talk louder, but then maybe I should readjust. If you have a minute, then I will try to readjust the settings. Let's see what we have here. Then I will adjust my microphone. I guess that's what I have to do. Audio here. Yes, yes, yes. Well, it looks quite all right here. Input volume. I can pump it up a little bit. So I hope this is getting. No, I cannot do that here. It's just not working. Okay. I will try to talk a little bit louder. So that is what I will do. Okay. We start a little bit over. Yes. So hopefully you get to see my screen. We're talking about sea level. Why would we bother about the sea? Well, as I said, it's more than. I cannot do it like this. I'm sorry. Uh, I will shut my telephone down now because this is quite annoying. I'm so sorry. Sea level. There's a lot of water, and why is the water important? I would say present day life, well, very much depend on the water. We have the influence on the weather, we have the influence on the climate, and we have all kinds of activities at the water, in the water, and we use it to transport goods and we transport people with it. So yes, um, we need to monitor what the water is doing and what it will be doing in the future. So, and that's where all these satellites become indispensable. And with all these satellites, we can look at temperature, salinity. I think the Aquarius plot on the bottom is about salinity, velocities, currents, and most importantly, yes, sea level. Especially if you are in a country or a city close to the sea, and maybe also level-wise close to the sea level, as we are in Holland, but as you are also, let's say, in Bangkok and the Gulf of Thailand. And if you talk about sea level, as I said, satellites, you immediately actually talk about altimetry, what we refer to as satellite altimetry. Basically, we measure the sea level with our altimeter uh, above reference ellipsoid, as we call it. interesting thing, part of that is the dynamic sea surface. So basically the currents we see. You have mesoscale variability. Uh, you have large scale ocean circulation with some applications there. Large scale variability, so it's referring to the climate. And well, basically with dynamic ocean models, we can actually also we measure the sea level, but we can also go into the interior of the ocean and say something about the vertical structure of the circulation. And then, yes, forecasting these mesoscale and large scale variability by assimilating them in models. And we want to monitor global sea level change. Talking about the altimeter, um, so what is it measuring? We have to actually start the first animation on the left. This is what the satellite is doing. It's actually sending pulses, radar pulses to the ocean surface. It transmits it. It gets reflected at the ocean surface, and it's received back. And what you receive back at the altimeter is a curve, which is basically it will repeat. Is a curve that looks like this orange curve, and we can change this midpoint of the leading edge. This basically gives you the sea surface height, and so that's basically the timing of the pulse, the time it needs to go from the satellite to the sea surface, and getting back to the satellite. We can get a bit more information from this returned wave. We have, for instance, the steepness of this leading edge, and that says something that is directly related to the significant wave height. So the waves you measure at sea. Then also the power returned, we call that the backscatter. That gives insight on the roughness of the sea state. So how rough are your waves, and that says something about the wind speed. And more wind, you get higher waves, you get a rougher sea surface, and that is also measured. So basically, typical three geophysical parameters. That is your sea level, that is your wave height, and that is the wind speed. And we already do this, let's say, from the early 90s with what we call low resolution mode. So that is the left, basically the left image video. There is like, well, basically that is 1 Hertz measurements. So that is along the track where the satellite goes. Every second there is a measurement. That looks quite frequent, but then already 7 kilometers have passed along the path, along the ground track. So we have a bit of a better instrument nowadays, which is referred to as SAR altimetry. And we get a very high resolution along track. So basically, this indicates the difference between this conventional altimetry and high resolution. Okay, so we're in a nutshell, again, what you can do with this returned wave, this returned echo from the sea surface. The epoch of the half height point gives you the range. The amplitude of the echo, the backscatter coefficient, so that's the dark green that gives you basically the wind, and then we have the slope, the red curve. No, it's not a curve. Let's say the red line following the slope of the leading edge of the wave, and that gives you the significant wave height. And you can say, okay, then that's that. Is that it? How you can use it? Well, it's still a bit more complicated. So yes, we measure basically with the radar altimeter the distance from the satellite to the. Let's see if I can get a pointer here. Let's do it like this. So maybe hopefully you can see my pointer here. So here we have the sea surface. Yes, it is reflected here. So what you measure is the range. Now, then you don't have the sea level yet. Basically, you want to have the sea level with respect to a reference. So that reference can be what we call a reference ellipsoid, basically an ellipsoid that closest fits the relief of the oceans. Um, if you have that, if you have the position of this ellipsoid, and you have to know exactly the position of your satellite with respect to the ellipsoid, and then you can basically subtract these two, and you get the height of the sea level, of the measured sea level. So basically, that is this r minus h, and we have then something called the marine geoid, and that's a bit of a static part, and we have the dynamic part. And the dynamic part of the sea surface, which is referred to as dynamic height. So that is this s. So n plus s is r minus h, and then you're not there yet. We need a lot of corrections. Basically, here we go from timing the pulse needs to be transmitted, to be reflected, and then get back on board of the satellite. In first instance, we say, okay, yeah, it's a radar pulse. It goes with the speed of light, but we go through a large part of the atmosphere, and that is actually delaying our signal. So we have to do a correction to this signal. So here's a bunch of all these corrections. So this makes it a bit more complicated. We have corrections basically directly on board of the satellite. So how the wave is interpreted. There's Doppler shift, there's oscillator drift, there's lots of things going on actually in the instrument. Then it goes through the atmosphere, so we have atmospheric refraction corrections, the dry troposphere as we call it. We have water vapor, so that's the wet troposphere. And we have also free electrons, so the electron content of the atmosphere. So we call that the ionosphere correction. We have also some correction to do if we are at the surface of the ocean. If you talk about waves, they are not perfect sinusoids, and actually the deviation of the waves from these sinusoids, they introduce an extra delay. So there's basically more power returned of this echo. Let's say from the troughs, and the peaks have less, so there's a bias there. We call that sea state bias. We also have to introduce that to our altimeter, and depending on what you want to measure, you might want to get rid of the geoid height. So then you only have the dynamic part of your sea surface, so directly an insight into currents. We have tidal contributions, ocean tides, solid earth tides, and we have atmospheric pressure loading. Basically, that is what works as an inverse barometer. If you have your atmospheric pressure, it will adjust a little bit the sea level. So we have that, of course, at the tide gauges as well. So yes, we have a whole bunch of these corrections, and not all of these corrections are well. They are known within a certain accuracy, and nowadays, well, that's quite amazing. If you let's say think that this altimeter, this satellite, is like 800 kilometers away from us or from the sea surface, and we can still make the measurement, let's say, within something like 1 to 2 centimeter, and that's of course amazing. If you introduce averaging over time and over places, then you can actually get the noise down a little bit, and you can have really better performance than that. So, well, you might think, why do we need a plot of the bottom topography of the ocean? Well, this is not bottom topography, what we see here. This is mean sea surface. So this is getting a whole bunch of altimeter measurements together, and we plot it, and it looks like this. So that's also quite amazing, because yeah, we think we see the ocean bottom. So how does that work? It's explained in this cartoon. So this is basically what the water level is doing. It works like like a leveling rod, as they call it. So it will shape, it will turn towards, let's say, perpendicular to what it feels on local gravity. So if we do have either a mountain, a sea mountain, or we have a more solid or denser material uh, beneath the ocean bottom, then basically you will get some of these plumb lines. They will orient towards what they see as the local enhanced gravity. So basically, it will take the shape of this. So you see a bulge wherever there is a sea mountain on the bottom, or when there is let's say an extra mass underneath the crust. So yes, mean sea surface. So this is the sea surface, not but it sort of looks like the bottom topography. And why does it look like the bottom topography? It is mainly because of this N. So this is what is called the marine geoid. That's the large contribution of local gravity. And this S is this can be tens of meters, and this S might be like a meter uh, in amplitude, so that you will not see this in a plot like this. But this is the part of the changing sea level because of winds, because of currents. So one way to deal with this data is, well, to take the average. If you have a good model for the geoid, you can subtract it, and then you have the absolute sea level with respect to the geoid. Now, same data, but now we subtract this average, and we actually only look at everything that is changing over time. We call that sea surface variability, and that gives a totally different picture. Here you have wherever there is enhanced variability in the ocean, this will show up in this plot with these more red and brown colors. And this is where all the larger currents are. There's lots of changes in these currents. They are meandering, so over time there's lots of changes. And you will see all these what we call western boundary currents popping up. And then you can of course do lots more with altimetry, but I would say mean and kind of standard deviation, and also look at trends. Is the sea level changing over time? So, and we see here a plot which has change in mean sea level. So here we have basically starting in the altimeter era with a satellite called TOPEX. And these are basically all the what we call the reference missions. It started all with TOPEX, and we get the JSON1, JSON2, JSON3. And nowadays we have the Sentinel-6 satellite as a successor to JSON3. So this is a satellite that flies the same ground track. Now there will be lots of well, let's say the variability you should see is in first instance is a seasonal cycle. So warming up and cooling down in summer, winter, and that is just a nice seasonal cycle. If you remove that from your signal, from your altimeter signal, your sea level signal, then you end up with this and average it over the whole globe. You can a thing like this, and that basically says that sea level is rising on average over the whole globe the last let's say the last 30 years or something like that. So there is, let's say, real evidence that this change is taking place. If we look at the whole tide gauge record, we started to measure sea level with tide gauges and already do that, let's say, around the late 19th century. And then we see here this red thing here, that is our altimeter era. And here we see also this, well, I wanted to say a nice curve, but yeah, basically this is not so nice, of course, because this means that indeed we are still to deal with rising sea level. But you can see that altimetry picked this up, this tide gauge signal. So we're all measuring more or less the same thing. Now, if you look at the surface trend, so in this plot here, we basically average over the whole globe. But if we don't average over the whole globe, but just look at point for point on the globe, so let's say a geographical distribution of sea level trend, then you get something like this picture on the left over, let's say, if we start in 1993 up to 2012. This is just an example. Of course, we can make newer plots now, but what it does show is that it's not a uniform rise. It's not everywhere the same, and it's not just depending on the location, but it's also depending on the time frame you look at. And so here we basically split up this time frame of 93 to 2012 in two parts, and basically you see also a change there. So yeah, so be aware that yes, there is a geographical dependence. There is also a temporal dependence. But yeah, you can see these El Nino things, the things that are changing a lot. So this is basically El Nino, what you're seeing here. This large red blob in the Pacific on the western side. Okay, a little bit back to yeah, what we measure or what we can measure. As I said, if you have a nice geoid model, you can subtract it from your altimeter measurements. So you get the dynamic topography of the ocean, and that relates directly to movements in the ocean, so to currents. So we need this marine geoid, and marine geoid. We saw this gray, almost like bottom topography plot, and I said no, it means sea surface, or I could also said it's marine geoid. It's predominantly marine geoid. It's an equipotential surface, as we call it. It means along this relief of the geoid, we feel the same gravity. So it looks like bumps and valleys in the ocean. Well, officially they are, but it doesn't cost any energy to go from a valley to a bump. It's an equipotential surface. And we need that to say something about the moment your surface is deviating from this equipotential surface. Basically, it starts moving. It starts moving from high to low, and then we have the Earth rotating. So we have to also deal with the Coriolis force. And that combination, this balance between going from high to low and rotation of the Earth, that makes it that the currents, as we have in the atmosphere, the currents and the wind, they will follow the lines of equal height or the isobars, the equal pressure. So we talk about dynamic height. Now, a way to do that is like the plot on top, where we measure something like conduction temperature at certain depths. And we have ships for that can measure that for us. So at different depths, you measure the conductivity of the water. That gives direct access to salinity and also temperature. And with that, we can build for every layer. We can build the contribution to the total topography. You can add that, and at the top isobar, let's say that is the ocean surface, you get these deviations as we see here. So if that is in meters, a few meters here. To do this, we need to go actually to a certain depth where we assume that everything is flat, that the isobars are flat, and then we can basically do this calculation. But we need many years of ship measurements, and you can see here also our western boundary currents, so the Gulf Stream here at Northern America, and the Kuroshio. So wherever these lines of equal height or equal pressure, when they are closer together, basically the gradient is steeper. If you go like this, so that means velocity is increased. Now with altimetry, basically you can have a plot like this, well, with Topex, this is from Topex, I think, or maybe one of the JSONs, but then we need like 10 days to gather the information for the whole globe. So in 10 days, the pattern in which Topex measures the sea level repeats. We call that a repeat period, repeat orbit. And in this case, it's 10 days. So basically, we can make this kind of plot or this kind of dynamic topography already after 10 days. So we don't need 50 years of ship measurements. So that's actually quite nice. Well, on the basis that we do have to know what is the geoid. So we have to have a very good geoid model. So that was a bit on altimetry. We also look, of course, at the tide gauges. Tide gauges, it's a bit different from altimetry. Yeah, well, it's different because it's closer to the actual sea level. But it's also, the satellite is not connected to the Earth. So basically free from that. And its reference is the reference ellipsoid. For tide gauge, it's different. It is attached to the land. So the reference is a point on the land. So with tide gauges, you would actually measure sea level with respect to land. So with respect to what the land is doing. The land itself can also move in a vertical manner. So yes, tide gauges measure sea level with respect to a geodetic benchmark. So connection to the actual height of the Earth, or let's say if you combine it with GNSS, you can actually also measure where your benchmark is and put that in the same reference ellipsoid frame as the altimeter, and then you can really start comparing. So how does these tide gauges work? So yeah, most common thing is that it's a float, so we're operated in a pipe or stilling well. Nowadays we have a bit of a more modern versions of that. So it can be an acoustic sounding tube or even microwave radar. So that's basically an altimeter, but then very close to the water and attached to the land. So so they move, the tide gauges, they move vertically with the land due to post-glacial rebound, tectonic uplift, subsidence. Subsidence can be by water extraction and stuff like that. So there can be things happening to the land, and basically the tide gauge goes along with that. Yes, often they are tied to, at least that is what we advise, to GPS, GNSS for absolute vertical datum transformation. Thing with tide gauges is, of course, they are close to the land. They are not uniformly distributed over the Earth. So they give not exactly the same view as the altimeter is getting, because that you will get a global view. What we do see is that they also record something like 20 centimeter over the last century. So that's let's say 2 millimeters per year. With the altimeter, watching the whole globe, we actually have higher values than this. We go to like 3 millimeters per year. And just checking the time, maybe I should speed things up. So this is a bit about how we tie all our measurements, the GPS measurements, the tide gauge measurements, and the altimeter. Basically, for that we need something called the geoid, or a kind of a vertical benchmark datum on the land. So just to connect what we measure with GNSS, what we measure with the satellite altimeter, and what we measure with the tide gauge. Bring that all together in, let's say, one reference system. This I will skip, but this is basically, I will distribute, or at least send the slides so that you can have a more closer look to it. This is basically explaining in more detail how all these things we measure, we see. We have, of course, the VLM, the vertical land motion from GNSS. we have the MSL, mean sea level, both from altimetry and tide gauge, and how we can tie that all together. So this basically this is referring to SF. So SF is what happens to the seafloor. And some of these things have a temporal dependence, and others we just take as a constant. Yeah, this is a bit of let's call it a commercial break, but I also want to actually show you that we have access to lots of altimeter data, and we are kind of proud that we have our own database. We call that RADS. This is just for information. I will not go into what RADS actually is. It's a database. It's where you choose all the corrections that are needed for the altimetry. But the nice thing of this database, it has all the current information from the altimeter satellites, but also all the backlog of whenever it started somewhere in the early 90s. And you can combine that for interesting studies. So this is just showing where to get that information. This is a bit on what we have, all our altimeter satellites, and the periods. Basically, this list is actually longer. It doesn't fit this slides. We nowadays have also Sentinel-3B, and we have the Sentinel-6A, and very soon there will be a launch in November of Sentinel-6B. So lots of data, we can do lots of things with it. I want to show you a few results for the Gulf of Thailand. Recently, we did a project research for ESA, where we concentrated on Cryosat. That is yet another altimeter satellite that actually goes quite north and south. So it's also basically an ice mission, but also a very good ocean mission. Why I show this? So this is just let's say a referral to a paper. The most important plot on this page is the bottom left, where we follow what Cryosat is doing with respect to the reference missions and how that changes over time. So yes, there is some wiggling, but I think the important part is the sort of trend we see here. And this is around, if we talk about Cryosat, within something like 0.2 or 0.1 millimeters per year. So that makes Cryosat also very useful for introducing sea level trends from this satellite. Sea level trend, well, that is around 3 millimeters per year. We will see that if you over the whole time span, it is, let's say, very stable. Then we can actually use it, and that is what is shown here. If we then directly go to sea level trend, but then for, let's say, for the whole world, based on Cryosat, then we have to look at the right-hand side of this plot, of this slide, and we compare it what we get from our reference missions, which we believe are, let's say, the best and most reliable there are, but we actually see no real large differences between these two plots. And here we have, if we measure from the start of Cryosat, so that is 2010, in this case up to 2024, we get a average value for the whole world of 3.8, 3.9 millimeters per year. So basically concluding that this Cryosat, under the typo here, so this should be Cryosat, constitutes a stable platform, so it really performs on par with the reference missions, and we can directly use it, and let's also then use it. For this whole time period, you can actually do a mean SLA, and SLA, sea level anomaly, is with respect to mean sea surface. Already a mean sea surface has been subtracted, so there's little, let's say, little information that is kind of sticking out, but you do see the information around the Antarctic, and we do have a bit of a difference. I mean, if the mean sea surface would be the exact perfect, the model would be perfect aligned with the data, then we should actually see nothing in this kind of plot. But we do see a few excursions, and that just means that was not present in the model. So, variability, we've seen that plot before, so this is just over this time frame 2010 2024, the variability of the ocean. We can also look at that this average mean sea level anomaly over the seasons, and we see differences appearing there. So for different seasons, different values for this mean SLA, and then you also see these features of the El Nino popping up. But okay, so this is not. We really have to go to the Gulf of Thailand, I guess. After this one, this is mean dynamic topography. This models and basically the mean sea surface model minus the best geoid model. You end up with the plot on the left hand side. We have to smooth this, and then we end up with the plot on the right. So if we want to look at dynamic topography, we basically have to add the right hand side figure to our sea level anomaly to get the total dynamic height. Okay, so here we finally go to the Gulf of Thailand. I'm just wondering how much time I have. I think we started a quarter past, so it's okay. I should be speeding up a little bit, but here we have for the Gulf of Thailand, we have the trend, so the slope, or let's say the sea level rise. Well, on average, it's all on the positive side. Well, positive, but actually meaning that yes, we are rising in the Gulf of Thailand, and over the cryosat period, this 2010-2024, we see for the area, the Gulf of Thailand area, like 2.3 millimeters per year. So at least it is lower than the global average. We can look at the mean, and we can look at the standard deviation. So the right is the standard deviation. So wherever it's not blue, there is more of a variation. Well, we know that the Gulf of Thailand is actually, there's a very strong seasonal cycle. It's going up and going down over the seasons, and that's basically what you see here as well. So if we look at currents, yes, so mainly you will see over a large part of the year. So over let's say the spring and the spring and the summer, this anticyclonic clockwise gyre. For the other let's say months, it's much weaker. That's basically what this is saying. We can just look at if that is also what we are seeing in our altimeter results. What we have here is a seasonal SLA in the Gulf of Thailand. So for each of the seasons, we have, well, we can actually see the changes. So we have high sea level in the fall and also in the winter, and we have low in the spring and in the summer. Now, if we add back, let's say the dynamic, the mean dynamic topography, you can actually see these gyres, and basically it works like this. Here we have the lines or colors of equal height. So basically, and we are at the north hemisphere. So that means that we have the lows on this side, highs here, then basically the movement of the water is like this. So it's indeed a anticyclonic cycle, a clockwise cycle. You can also say that it looks stronger, let's say in the fall and in the winter. which would say something different than the previous slide, but that's not the case. So basically, we here go almost over the whole color legend. So this slope is much steeper than the slope we see here. This is just because of the colors, and now red looks bad, but this going from here to here is less of a difference than going from here to here. So yes, it is stronger in the spring and in the summer. Okay. If we compare, and we have different geodetic techniques. We have the altimeter and the salt. We have the tide gauge, the TG, and we have the GNSS, which gives the vertical land motion, which is the VLM. We kind of tend to say, if you have your altimeter, you subtract tide gauge, and tide gauge is sea level with respect to the land, minus land. Then you have minus land, so that gives you directly the land motion. You can make more of these combinations, and it gives us the opportunity to combine these measurements, and also where we have all of these measurements to actually calibrate or validate these measurements. And if the validation says it's okay, or it's perfect, then of course we can, everywhere where we actually missing one of the signals, we can with these equations get the missing signal. But how does that work? I mean, does it work? And therefore we have to, let's say, if we look at the trends, and so what is the trend in the vertical land motion? What is the trend in sea level? Then we have a few things here. So we have RSL, so that's basically relative sea level, and that directly comes from tide gauges. Then we also have global sea level, which comes from altimetry. So how can we then combine these? So basically, sea level is a combination of mass or mass redistribution and something what we call stereodynamic trend, and that comes from just water heating up or cooling down, and then this changes the sea level as well. So sea level is basically a combination of mass or mass redistribution coming from rivers, coming from ice that is melting, and also because of changes in the temperature, which makes the water expand a little or contract a little bit. And then we have something called the GIA, so it's a global isostatic, the post-glacial rebound. And they are not the same for let's say the altimeter sea level and the tide gauge sea level. So we have these things called here. So sea level, yes, with respect to the land, and this is all taken at a position R. And if we combine this, so basically if we do something like altimetry minus the tide gauge, then basically you can do, let's say, the math yourself. There is some residual what we don't know. We just say, oh, it's either small or it is the same. But if we do that, then in the end, yes, then we see that indeed salt is minus TG is giving the VLM. Now that is true, we actually came to that conclusion for a study for the sea level near Phuket, and this is in a paper. So this is a referral to the paper. So I actually invite you to look at the paper. But I think for us it's more important to look at the plots, and we have on top that what the tide gauge is measuring near Phuket, and also what the altimeter is measuring. That's the middle figure. And then we have also the land, what is measured by the GPS or the GNSS. Now, interesting thing here is, of course, if we look at this VLM, we see a steady growth in the beginning, and then there was this gigantic earthquake. So this was this Sumatra Andaman earthquake in in 2000, the end of 2004, and that changed a lot. So there was not a jump in the vertical, but it did, let's say, change in how the sea level behaved, and this is what we see now. This was not felt, or is not felt, by the altimeter, but let's say if you make a combination, and this is what we see. We basically see a similar pattern, be it kind of mirrored, uh, happening in the tide gauge. Well, the tide gauge is connected to the land, so it actually should follow the land. So if you do here this salt minus T tide gauge, then basically yes, you come up with this kind of curve. So the amplitude is not exactly the same, but the behavior is kind of similar, and that was of course a very nice outcome of this research. Basically, what's happening here is that finally it will level out here, and then it will start going back in the same manner as it was before this 2004 earthquake. We digged into that a little bit deeper, looked at the models. We actually fitted a yearly signal together with trends, and here we fit an exponential decaying thing, and we make these combinations where we have salt minus dg, so getting the VLM, etc. Salt minus GPS, giving you kind of a tide gauge signal, and tide gauge minus VLM, giving you a kind of a altimeter signal. And basically this fitted quite nice. The only change is, well, the difference is that we have a kind of a somewhat more complicated, well, it's an annual signal, and basically also a half yearly cycle that is not in the land motion, and also what I said, the amplitude is not exactly the same. So we are still trying to figure out what is the explanation for that, but it is nice to see that these equations do work. Yeah, I think I really should wrap up now, but there are a few points in the Gulf of Thailand, or in this case the Andaman Sea, so this is our Phuket station. For this area, okay, it's around 2 millimeters per year, and we look here at the sea level and also the tide gauge. Now, it follows quite nicely, and of course, if you subtract this minus this, you get the vertical land motion. Now, we did this in a few places. Okay, so this is not Thailand, but this is a little bit into to Malaysia, but it's the Gulf of Thailand, I guess. So we do a bit of the same analysis for lots of tide gauge stations around Malaysia, and yeah, we basically get this. You get the same idea. It really fits very well. This salt minus tide gauge giving the vertical land motion. Okay, back in Thailand, Komatapon. So we go a little bit up north. Sorry. Here we have Kolak, and then we go into the inner Gulf, and also this is quite a nice comparison. Good, then yeah, I think we are more or less at the end. So conclusions about the Gulf of Thailand, sea level variations. We have altimeters showing that the absolute sea level, the ASL in Southeast Asia, is rising. Due to climate change, I think that is undisputable. We see for Thailand, on average, over this, let's say, 14-year period of crisis, 2.3 millimeters per year in the Gulf and 1.8 in the Andaman Sea. And I say the good news might be that this is lower than the global average of 3.8 millimeters per year. So whether this is a threat, this rising sea level, depends on what actually the land is doing. So what the vertical land motion is, that can be obtained by GNSS or by subtracting salt and tide gauge. So basically, that should give the same information, and that is what we saw. Most of Thailand experienced land subsidence due to close-by megathrust earthquakes and groundwater extraction, and that together increases RSL. So that is maybe the somewhat less good news. Having all the techniques at the same time in place, this can be used to calibrate any of the measurement systems, what I showed, and that's nice that all these space geodetic techniques can be applied everywhere on the globe, and they're almost always available. So that's a very nice aspect of that. So they are indispensable for ellipsoid-based vertical datum transformation and give insight in both the relative sea level and also in the absolute sea level. Okay, so this ends my presentation. So yes, it is about perception, but I think the better quote is, it is about reference. What is your reference to say something about all these changing services? Okay. Not sure if there are any questions. Please let me know.
Thank you, Mark.
You're welcome.
So we running a little bit late, so we would like to go into another next speaking. So hope to see you again. Yeah, yeah. Thank you so much. So our next speaker is Milan Lasexki from University of Leeds, UK. He will talk about deformation of Bangkok area from the INSA study. So if Milan is online right now, I cannot hear you. Have you can open the microphone? Can you hear me?
Yeah, so the microphone is open. Do you hear me?
Oh yeah, I already hear you. Thank you, Milan.
Okay.
So the floor is
Great.
yours. Thank you.
Thank you very much. Ladies and gentlemen, I appreciate your invitation, and obviously my condolences for your loss. Let me bring the slides, if I can share the screen, which I unfortunately don't see the button. I think I'm not. Oh, okay. Yeah. Okay. Now it works. Okay.
Okay, I can see your slides.
Thank you. Okay. So my presentation today will be similar to the previous presentation, and it relates to the deformation of the Bangkok area as we were observing them using the satellite synthetic aperture radar interferometry. So I come from COMET, the Center for Observation and Modeling of Earthquakes, Volcanoes and Tectonics. That is a group of universities, and I reside at the University of Leeds. Okay, so Sentinel-1, just very briefly, is a constellation of two synthetic aperture radar satellites that acquire images in subpolar or fly in subpolar orbit. And it allows for interferometric measurements within 5.5 centimeter wavelength. Therefore, it has a millimeter level sensitivity on radar phase delay. And the radar phase delay is caused by deformation and atmosphere primarily. So Sentinel-1 mission is active since the end of 2014, and it has a revisit time of either 6 or 12 days, depending on the time period when there was activity of one or two satellites within each track. So I show on the picture that there is some sort of emphasis, reasonable emphasis on the tracks, as the satellite, by its design, is not looking directly to nadir. So the measurements are measurements in some inclination. So we work with some incidence angle 23 to 45, which is a broad range of angles, but it remains the same overall the whole time period. And it measures within some angle. So it's not sensitive only to vertical motion or deformation. Yeah, and as there are subpolar orbit passes, in one pass, we call it ascending, the satellite flies and it's right looking, therefore the incidence angle is actually from the west, and opposite is true for the descending pass when the satellite flies from the north to the south. Okay, so we have two different geometries. Now, within our group, we develop Lixar system, which is a system that generates open interferometric data globally from the satellite mission, and it's primarily focused on tectonic and volcanic areas, but we do some exceptions. So what we do is we distribute 100 meters resolution interferograms as open data, so you can visit the portal, download the data for any of the frames that we process. Plus, we also distribute tropospheric correction based on model. And additionally, for this project, we generated also 30 meters resolution interferograms that cover Bangkok city. Now, I show example of one interferograms, and that interferogram show basically colors, and the color scale is going from minus pi to plus pi. It's a measurement in radians, but you can convert that radians that speak about delay basically into millimeters, assuming that it is purely deformation. In this particular case, you can see that this probably is not any deformation of that would be 9 centimeters, but it's most probably atmosphere. So atmosphere plays a really strong, significant role, and if we would have only a couple of images, we would not be really able to separate the signals from the deformation or the atmosphere. Okay, what we do? So we also prepared the LixBus time series processing software that performs inversion of large set of generated interferograms into the time series. And this is an open source tool. It auto downloads data directly from our system, and it was originally developed by Morishita, but it's further developed by the Comet team. Okay, so that's very briefly. Now, regarding the Bangkok area, this is our input of the Comet Lixar data. We have data from two frames. One is descending, D, and second is ascending. And we form a network of interferograms where we connect each of the acquisition with several. By default, it's set to 5 consequent connections are generated, and that's then inverted per epoch, and we do it primarily to avoid potential errors with some necessary technical procedures like phase unwrapping. Plus, we add the Gauss tropospheric correction. Okay, here I show some previous result showing how the INSAR outputs or the primary output that is the linear trend of the deformation within the whole time look like. So you can see the satellite flies here in the ascending mode. It flies from the south to the north and looks to the right and measures and the data is actually I didn't mention that this data is 2015 to 2021. So what you see is the linear deformation trend during the 6 years basically. We can zoom in that previous processing results, and we already see deformation zones. And as this deformation trend is based on the inverted time series, we can see the time series of both frames. The ascending here is in red, blue is the descending, and they are both referring to one pixel, and each of the pixels have that time series that we can further investigate. So, but before I will show the current outputs, I would like to mention about the previous INSAR processing results taken from the literature. Basically, we prepared this presentation together with Professor Andy Hooper, that is behind the first analysis using little different technique, persistent scatterers INSAR, from 17 radar images of the ERS satellites that was active in the last century. And here we see basically two large ball spots of the highest deformation. And again, we could see the time series plots showing really strong trend of the subsidence. Then there was another project using RadarSat-1 interferometry in 2005 and 2010. But this didn't cover the whole region. It was focused on the Bangkok area by Anufao. And here I will show some spots just to see if there are any particular changes in current processing results, like current time. And it seems that those subsidence balls quite disappeared. Here you can see the Sentinel-1 INSAR result from those 6 years. And here we could use 244 radar images, which is a large number. And you can see the scale fits the continuation of that same point where there is no subsidence anymore. Okay, still there are some areas that show strong subsidence, but these are outside central Bangkok. So these results that I show you are these were strongly downsampled into 1 × 1 kilometer. Now I was focusing on the processing of Bangkok city itself with the reprocessed data, and I generated interferograms in higher density than the previous, just to avoid potential errors. And these interferograms were generated in 30 meters and then downsampled to 100 meters. So again, I was showing these particular slides previously. However, you can get the idea of the coverage. These are all the pixels except of very high erroneous ones, as we still have some downsides of the techniques, but we can identify the potential errors and mask it. And because we have two tracks, one is ascending, second is descending from different geometries, we can perform so-called decomposition into the vertical, primarily vertical, and the eastwards. And here you can see the map already transformed into the vertical velocity and preliminarily tied geodetically, but I will speak about that a little later. Okay, so what can we see here? There are still spots in Bangkok area that show strong trend of subsidence. This is data. I probably didn't mention it, but this is data of covering 8 years. So these are all linear trends from 2015 to 2023, and we can see several spots, several areas that constantly have the subsidence. However, if you compare it with the previous result, the main subsidence areas remain, but the rate is significantly smaller. Okay, so that's perhaps good message. There is still ongoing subsidence locally, but it's significantly smaller. Now, as we are primarily interested in the absolute reference frame, we have performed the reprocessing, and now we have the time series until the end of 2024. And we added geodetic tiling to the absolute reference frame in a preliminary fashion, which basically means we use two existing permanent GNS stations that are installed at the top of tall building in both cases, and we use the vertical velocities or general velocities that we transform into the line of sight, but there's technical detail. And we basically took the weighted average to tie our INSAR results to the absolute reference frame, as the INSAR data are reference in time and space. That's again from the technical possibilities perspective. So here you can see basically the same image as before. Apologies for the flipped color scale. And here you can see the absolute vertical average velocity map. So after the tying and getting the GNSS data, of course, we tried to compare the quality, and actually I was not focusing that much into the overall quality that is that should be anyway within the margin of 0.6 millimeters per year, 1 sigma. But what I show here, or what I did further, was I tried to split that whole time series into 3 groups. Each group has a coverage of 3 years. So we have some 4-year periods identified as shown. And I got the average values from the GNSS stations that slightly differ, but it's in absolute reference frame is around 3 millimeters per year. And after the time, I checked for the velocities for all those 3 time period between these two GNSS stations that should be exactly the same, right? As we work within um, similar level of accuracy, or yeah, but they differ. Especially the last time period that is set to 2023. It's in fact it's 3 years average, and it differs by 1 millimeter, and that can be for different reasons. As we should see the GNSS station as a proxy, as we are performing average, and also the GNSS stations between them might have also some discrepancies. What is measured there is basically the top of the building, right? But we are here averaging all the objects within 100 times 100 meters, and that can cause that discrepancy. However, still we should be careful about interpreting especially the last time period. And I say that primarily to avoid jumping into conclusions once you will see following slide. So as I mentioned, I took those 3 temporal subsets of the INSAR data, and I decomposed per those 3 time periods. So we have, each of them have a smaller data set than the original 244 images, and therefore the accuracy is lower. However, we still, especially with the possibility of atmosphere playing role, for example, residuals of atmosphere probably, but we still see the same zones of the deformation. We can track them in time, and what you most probably would notice is this area that got suddenly blue in the last time period. And if we have a look on some, this is example of 1 pixel, and indeed in that pixel the time series show increase of subsidence after, let's say, since 2022. So the further investigation is out of the scope of the project, but I think it's worth investigating what is happening. So in summary, the INSAR measurements are more reliable with increased number of radar images. We present 2 different scaled outputs focused on the whole region and over Bangkok only from Sentinel-1. And data show Bangkok is more stable with locally subsiding areas, but some regions outside or at the edge of Bangkok appear to start subsiding since 2022 from the data. Okay, I thank you for attention, and I'm welcoming questions.